Humanity has always searched for new worlds, but some were never meant to be visited. A planet so large it could swallow every other world around it, a place with no solid ground and storms that never end. From a distance it looks like just another planet, but up close, it is something else entirely. This is Jupiter. Jupiter is not just the largest planet in the solar system. It is larger than all the other planets combined. Its mass is more than twice that of every other planet together. If Jupiter had been slightly more massive, it might have become a star. But it never reached that threshold. Instead, it became something else, a gas giant. Jupiter is composed primarily of hydrogen and helium, the same elements that make up the Sun. But unlike Earth, it has no solid surface. What appears as a surface is actually the top of its cloud layers. Descending into Jupiter does not lead to ground. It leads deeper into atmosphere. Pressure increases continuously. Temperature rises. At great depths, hydrogen transitions into a metallic state, a form of matter not found naturally on Earth. Jupiter is not a place. It is a structure. A massive, layered system of gas under extreme pressure. Jupiter's influence extends far beyond its visible size. Its gravity is immense. It affects the orbits of other planets. It shapes the asteroid belt. It captures and redirects comets. Some scientists believe Jupiter has played a protective role. By deflecting or absorbing incoming objects, it may have reduced the number of impacts on Earth. But this role is not simple. Jupiter can also redirect objects inward. Its gravity can both shield and threaten. It is a dominant force in the solar system. Its presence has influenced planetary formation from the beginning. Without Jupiter, the solar system might look very different. Planetary orbits would shift. Impact rates would change. The architecture of the system itself would be altered. Jupiter is not just another planet. It is a regulator. Jupiter has the strongest magnetic field of any planet in the solar system. It is thousands of times more powerful than Earth's. This magnetic field creates a vast magnetosphere. It extends millions of kilometers into space. On the night side, it stretches even farther, forming a tail longer than the distance from Earth to the Sun. This magnetosphere traps charged particles. It accelerates them to high energies. The result is intense radiation. Radiation levels near Jupiter are extreme. They are dangerous for spacecraft and would be lethal to unprotected humans. This environment makes exploration difficult, yet it also provides valuable data. Studying Jupiter's magnetic field helps scientists understand planetary dynamos, the processes that generate magnetic fields. It also reveals how planets interact with space environments. Jupiter is not just large, it is electrically active. Exploring Jupiter requires specialized missions. The spacecraft Juno currently orbits the planet. Juno follows a highly elliptical orbit. It passes close to Jupiter, then moves far away again. This orbit reduces exposure to radiation. Juno's instruments measure gravity, magnetic fields, and atmospheric composition. It has provided new insights into Jupiter's interior. Data suggests that Jupiter's core may not be solid. Instead, it may be diffuse, partially mixed with surrounding layers. Juno has also captured detailed images of the planet's poles. Unlike the familiar banded structure, the poles are chaotic. They are filled with cyclones, large organized storm systems. These discoveries show that Jupiter is more complex than previously thought. Humanity is not just observing Jupiter. It is measuring it. And with each orbit, new details emerge. Among all atmospheric features in the solar system, one stands out: the Great Red Spot. It is a storm larger than Earth, and it has been active for at least 300 years. Unlike storms on Earth, which form and dissipate within days or weeks, Jupiter's Great Red Spot persists. Its rotation is counterclockwise, driven by pressure differences and surrounding jet streams. Wind speeds within the storm exceed 400 kilometers per hour. The storm's color, a deep red, is still not fully understood. It may be caused by complex chemical reactions involving sunlight, ammonia, and other atmospheric compounds. Over time, observations have shown that the Great Red Spot is shrinking, but it remains immense. It is not a static feature. It changes shape. It evolves, yet it does not disappear. This persistence reveals something fundamental about Jupiter's atmosphere. Energy is continuously supplied, and there is no solid surface to disrupt the system. Storms do not weaken by interacting with land. They continue. Jupiter's atmosphere is organized into alternating bands. Light-colored zones and darker belts wrap around the planet. These bands are not static layers. They are dynamic systems driven by powerful jet streams. Wind speeds in these jets can exceed 500 kilometers per hour. They flow in opposite directions in adjacent bands. This creates strong shear forces. The result is turbulence. Clouds stretch, twist, and interact. Storms form at the boundaries between these bands. Unlike Earth, where weather systems are influenced by continents and oceans, Jupiter's atmosphere is uninterrupted. There is nothing to slow or stop the flow. The energy driving these motions comes from both solar radiation and internal heat. Jupiter emits more energy than it receives from the Sun. This internal heat contributes to atmospheric motion. The bands are a visible expression of deeper processes. They are the surface signature of a dynamic interior. Jupiter is not silent. Within its clouds, lightning flashes. These lightning events are more powerful than those on Earth. They occur deep within the atmosphere where water clouds are believed to exist. For a long time, it was uncertain whether Jupiter had enough water for such processes. Data from Juno confirmed the presence of water in deeper layers. This allows convective processes similar to thunderstorms on Earth. Warm material rises. Cool material sinks. Energy is transferred. Lightning is the visible result of these interactions. But Jupiter's storms are not limited to the upper atmosphere. They extend deep below the cloud tops, hundreds of kilometers into the planet. This depth makes them fundamentally different from Earth's weather systems. They are not surface phenomena. They are structural. Jupiter's poles are unlike its equatorial regions. Instead of bands, the poles are chaotic. They are dominated by cyclones. Multiple large cyclones cluster together in stable patterns. At the North Pole, a central cyclone is surrounded by several others arranged geometrically. These structures rotate but remain organized. This behavior is not fully understood. On Earth, cyclones interact and often disrupt each other. On Jupiter, they coexist. They form stable systems. This suggests different atmospheric physics, different energy balances, different boundary conditions. Jupiter's poles reveal that even after centuries of observation, the planet still holds mysteries. It is not fully understood. It is still being measured. Jupiter is not alone. It is surrounded by a vast system of moons. More than 90 have been identified, but among them four stand out. They were first observed by Galileo Galilei in 1610. These are known as the Galilean moons. Europa, Ganymede, Callisto. Each is a world in its own right. Each follows a different path of evolution. Together, they form a miniature system, orbiting a giant planet instead of a star. Studying these moons is not just about Jupiter. It is about understanding planetary systems as a whole. Io is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions. Volcanoes eject material hundreds of kilometers into space. This activity is driven by tidal forces. Jupiter's gravity pulls on Io, so do the other moons. This creates internal friction. Heat builds up, rock melts, volcanoes erupt. Io does not have stable mountains or long-lasting surface features. Its surface is renewed continuously. It is a world defined by energy and motion. Unlike Earth, where volcanism is part of a broader system, Io is dominated by it. Europa is one of the most important targets in the search for life. Its surface is covered in ice. Beneath that ice, evidence suggests the presence of a global ocean. This ocean may contain more water than all of Earth's oceans combined. The surface of Europa is marked by cracks and ridges. These features indicate movement beneath the ice. Tidal forces from Jupiter generate heat. This heat may keep the subsurface ocean in a liquid state. If water, energy, and chemistry are present, the conditions for life may exist. Future missions aim to study Europa in detail. Among them is the Europa Clipper. Its goal is not to find life directly. It is to measure the conditions that could support it. Europa is not just a moon. It is a possibility. Ganymede is the largest moon in the solar system. It is larger than the planet Mercury. Unlike any other moon, Ganymede has its own magnetic field. This suggests a partially molten core. Its surface shows both old cratered regions and younger, grooved terrain. Callisto, in contrast, is heavily cratered. Its surface is one of the oldest in the solar system. It shows little evidence of internal activity. It has remained largely unchanged for billions of years. Together, these moons represent different evolutionary paths: active, inactive, layered, frozen. Jupiter's system is not uniform. It is diverse. It contains worlds at different stages of development. This diversity makes Jupiter more than a planet. It is a system.